Hello, I am Dr. Rashmi Deshpande. This is the second lecture of the series Atomic and Molecular Physics. We are going to study the Schrodinger's time independent equation for hydrogen atom, and we are going to solve it to derive the hydrogen atom wave function as well as the possible energy values for the hydrogen atom. We are going to derive the Schrodinger's time independent equation for hydrogen atom in spherical polar coordinate system. So, let us start discussion with the spherical polar coordinate system. After that, we are going to see how to derive Schrodinger's time independent equation in 3 dimensions in spherical polar coordinate system for hydrogen atom, and then we will solve the Schrodinger's equation for hydrogen atom by the method of separation of variables. So first, what is polar coordinate system? We all are familiar with the XYZ coordinate system, that is Cartesian coordinate system. We are going to use spherical polar coordinate system for deriving Schrodinger's time independent equation for hydrogen atom. The reason is electrostatic potential which is experienced by this electron is spherically symmetric potential. So therefore we are using the spherical polar coordinate system. So first of all, we would like to see what is the relation between the two coordinate system, that is Cartesian coordinate system and spherical polar coordinate system. So first of all, consider the diagram where this XYZ coordinate system is shown. O is the origin of the coordinate system. P is any point in space having coordinates XYZ. Let us consider that its spherical polar coordinates are denoted by r, theta, phi. We are going to see how we can convert XYZ to r, theta, phi and vice versa. So just draw a line joining origin and the point P. A vector from O to P, that is r bar, is called as the position vector of point P with respect to origin O. Theta is the angle made by the position vector with respect to z axis. Okay. Draw a perpendicular PL on the xy plane. Join the origin O with L. So OL is a line in xy plane. So PL is also perpendicular to OL. The angle made by OL with respect to x-axis is angle phi. So now we know that P has coordinates XYZ which can be obtained by dropping perpendiculars on the respective coordinate axis, and R, theta and phi are shown in this particular diagram. Now let us derive the relationship between these coordinates. First of all, the easiest one is the Z coordinate. You can see here that if you drop a perpendicular from point P on Z axis, okay, then the foot of the perpendicular from point P on Z axis, the foot of the perpendicular and origin O, the distance between these 2 points will be equal to Z. Okay, so in this particular diagram you can see that the line PL, which is perpendicular on xy plane, this is also of the same length as the Z coordinate. Okay, and so it is parallel to Z axis, you can see, because it Z axis is also perpendicular to xy plane, PL is perpendicular to xy plane, so Z axis and this PL, they are parallel lines. So OP will be a traversal to these parallel lines. So this angle theta and this also will be angle theta. Okay. So in the right angle triangle OPL, angle PLO is a 90 degrees angle. Though in this particular diagram you cannot see that 90 degrees angle because it is a two-dimensional figure which we have drawn. Okay, so PLO, this angle will be a 90 degrees angle, and this R bar will be the hypotenuse of the right angle triangle PLO. So from our trigonometry we know that cos of angle is equal to adjacent side divided by hypotenuse. So adjacent side means this is the adjacent side for this angle theta, hypotenuse is r. So z is equal to r cos theta. So we have obtained this particular relationship. Then r will be equal to x square plus y square plus z square, which is equal to length of the radius vector. This also we know because we know that if a point P is having coordinates x, y, z, then its distance from the origin is given by under root of x square plus y square plus z square. So now we have obtained relationship between r, x, y, z coordinates, theta and x, y, z coordinates. The remaining coordinate is phi. So how to obtain that relationship between phi and x, y, z coordinate? So for that, let us draw perpendicular from L on x-axis as well as on y-axis. Now as we have learned that z is equal to r cos theta, similarly we can see that in this particular diagram, rho, that is equal to distance between O and L, is equal to r sin theta, because OL is opposite to this angle theta, opposite side to angle theta. Okay, so rho is equal to r sin theta. So in this right angle triangle, see, from L we are drawing a perpendicular on x-axis. So this angle is a right angle. Okay, this is a 90 degrees angle. So therefore this is going to be the hypotenuse. Okay, OL is the hypotenuse. So this hypotenuse multiplied by sin phi, r sin theta sin phi, by, because this is the side opposite to the angle phi. Okay, and what is the length of this particular side? It is nothing but the y coordinate. Okay, why? Because from L, if I draw a perpendicular on y-axis, okay, then distance between O and this point is the y coordinate. Similarly, distance between L and this point is nothing but the y coordinate. So y is equal to r sin theta sin phi. Similarly, you can see that x is equal to r sin theta cos phi, because from O up to this point, this is the x coordinate and it is same as this side. Okay, so x is equal to r sin theta cos phi. So we have obtained the three relations for r theta phi in terms of x, y and z coordinates, and for x, y, z, these are the relations in terms of r sin, r theta and phi. Okay, for obtaining the phi coordinate, what we have done, we have just taken ratio y upon x, that will be equal to tan phi. So phi is equal to tan inverse of y upon x. Okay, so these are the three relations, rather 6 relations which show us the interconversion between Cartesian to spherical polar coordinate system and vice versa. Okay, how to write the Schrodinger's time independent equation in spherical polar coordinate system? We know that we can write down Schrodinger's time independent equation in 3 dimensions in this fashion: del square psi plus 2m upon h cross square E minus v multiplied by psi is equal to 0. This is Schrodinger's time independent equation in 3 dimensions, where del operator is a vector operator which is written in this fashion: del by del x I cap plus del by del y j cap plus del by del z k cap, where I cap, j cap and k cap, these are the unit vectors along x, y and z axis respectively. Please remember that though the cap are not shown above the vectors I, j, k, but still you have to remember that these are unit vectors. Okay. The Laplacian operator in Cartesian coordinate system, that is nothing but the del square operator. It is the self dot product of the del bar operator. Okay, so it is a scalar operator which is written as del square by del x square plus del square by del y square plus del square by del z square. This operator in spherical polar coordinate system can be written in this fashion. If you want, you can just check it by using the interconvergence as we have seen in the previous slide. You can use the interconversion and you can derive this del square operator as 1 upon r square del by del r of r square del by del r plus 1 upon r square sin theta del by del theta of sin theta del by del theta plus 1 upon r square sin square theta of del square by del phi square. Please remember that the operator is not useful alone. You have to use this operator along with the function. The operator will operate on a function and then you will get a meaningful result. Afterwards, we are going to see how to use this del square operator to obtain this type of Schrodinger's time independent equation for the hydrogen atom. So we will use this del square operator. We will use the potential for the electron, potential experienced by the electron in hydrogen atom, and then we will write down what is the Schrodinger's time independent equation for hydrogen atom in spherical polar coordinate system. That's all for today. Thank you very much for patient listening.